So again, today we're going to look at 1.2, and we're going to look at applications. Now with these, I'm going to be picking questions from our textbook. We're going to read these. We're going to look at each part of it, and we're going to try to see how we would set up the equation, solve it, and then make sure that we answered the question correctly. Many cases you solve it, but what you solve isn't the exact answer. You may have to take it and plug it back in to get what you want. And we always want to also make sure that we label our answers in the correct units, if it has units. So we're in 1.2, and we'll start with a geometric figure problem. But before we do that, let's take a moment just to talk about units and how units are going to work. Okay, so we're going to look at units. Now, when we label things, we have to use the correct unit. When we talk about units, the first thing we're going to look at is we're going to look at the base units. And what I mean by the base units, those are going to be things like inches, yards, feet, miles, anything that you can measure. So these are my base units. And where do we have base units at? Well, we have base units in the perimeter, in a length, a width, distance. Those are all going to be measured in the base unit. So if we can measure it with a ruler, or if it's like a distance, that's going to be in the basic unit. So depending upon what it is, if it's a rectangle that we made, it might be in inches, might be in feet, might be in yards. If it's a distance that we drive in our car, all right, that might be in miles or kilometers. So it could also be in kilometers. But these are going to be the basic units. Now, once we use those, then we look at the square units. And when do square units come into play? Well, square units are going to be an area. So when we talk about square units, that's things like square inches, square feet, square miles, maybe even square kilometers. And where do we use square units? Well, square units are going to be used in terms of area. So anytime we have an area or a surface area, whenever we have one of those, we're going to have to be labeling it with a square unit. I think it's just helpful to take a moment to talk a little bit about the measurements of the units. And this also helps us see where it came from. If I see something has a square inches on it, I know it came from an area automatically. So when we talk about square units, it's either area or it's a surface area. Then we've got cubic units. Okay, and when we talk about cubic units, that's going to be cubic feet, cubic inches. We could have cubic centimeters. Those are all cubic units. Now, when do we use a cubic unit? Well, cubic units are going to be mostly in volumes. So when we talk about a volume, it's going to be measured in cubic units. And so things like the displacement of your car engine, it's going to be in either cubic inches or cubic centimeters. Whenever it's a cubic unit, it's in volume. Now, something else that we can use for volume is liters and milliliters. So they are also volumes. We also have a rate of speed. So let's talk about that next. So you can have division for a unit. You can have miles per hour. You can have meters per second. You can have feet per second. Anytime you have a distance divided by a time, that's going to be a rate or a speed. And there's different ones depending upon what it is. Normally we think of miles per hour or kilometers per hour. Right? Those are speeds, but there can also be meters per second or feet per second. And if you're looking at something like the speed of a bullet, you might look at feet per second. But anytime we talk about a rate or a speed, it's always going to be a distance divided by a unit of time. And we all know what time is. Time can be measured in minutes, seconds, days, however we need to break it down. But I just wanted to take a moment to kind of cover those basic units. So when we see them in a question and we see a cubic unit, we automatically know that that came from a volume. So now let's go ahead and look at some of these applications in 1.2. And we're really going to focus on reading them and trying to identify the different parts, because there's lots of different parts. Sometimes we may have to draw a figure to help us with these, but let's start on page 119 with question 15. So we're going to start with 119, question 15. And I'm going to put it up on the screen, and we're going to spend a moment reading the question. I always like to read through it once, and then after that we go through and identify the different parts. So let's look here at question 15. The perimeter of a triangular plot of land is 2,400 feet. 2,400 is in feet. Why? Because that came from perimeter. We can measure the perimeter. That's why it's in the base unit. The longest side is 200 feet less than twice the shortest side. The middle side is 200 feet less than the longest side. Find the lengths of the three sides of this triangular plot. So first off, we need to think about what we're looking at. So this is a geometric figure. And we're looking at the perimeter. Now, what's the perimeter? Perimeter, by basic definition, is going to be adding up all the sides. It doesn't matter what figure it is. Whenever we say perimeter, we simply add up all the sides. And in this case, we are looking at a triangle. And a triangle has three sides. So let's start with that. So we know the perimeter is the sum of all the sides, and we're going to be working with that. So that's our basic definition. And we're looking at a triangle. And the triangle has three sides. So when we talk about this triangle, they're all going to be different. And the triangle has three sides. We're going to say we have a short side, a middle side, and then we have the longest side. So that's what we know. Now, do we know anything about the perimeter? Yeah, it gave us the perimeter, and what was the perimeter with the number? What was the perimeter number-wise? It was 2,400. Now, I'm not going to put the feet on until the very end. What I always like to do with the units is I always like to keep the units until the very, very end. That way, we don't have to worry about having extra things. So at the end, we'll make sure we label it with the units, but right now we're just working with them so we don't use them with the numbers, so we don't write down the units. So what we've got for our perimeter is we've got 2,400. Okay, so we know perimeter is sum of all sides. We've got that 2,400. We're looking at a triangle. We could draw a picture of a triangle. You can do that if you want to. In this case, we really don't need to. Now, what I like to do is I like to label these in terms of words and then rewrite it with the variables. I think it's easier to understand if we start with words rather than just going straight to the variables. So when I look at this, it says the longest side is 200 feet less than twice the shortest side. So the longest side is going to be 200 feet less than twice the shortest side. So that's going to be 2 times the short side minus 200. Okay, is everyone okay with that? We're going to put the variables in later on. But right now we're just going to use words, and then we'll translate this into variables in a moment. So the longest side is 200 feet less than twice the shortest. The middle side is 200 feet less than the longest side. Okay, so that's what we've got there. And then one of these we know nothing about. And it doesn't tell us anything about the shortest side at all, does it? So that's going to be our variable x. Now we're going to rewrite this with only the variable x. So let's go ahead and rewrite this with the variable x. And so we have the short side, which is x. We have the middle side, which we'll come back to in a moment. And what about the longest side? What is it? It's twice the shortest side, so that's going to be 2x minus 200. Okay, so we've replaced that shortest side with x. And then what about the middle side? Okay, the middle side is the longest side minus 200, so that's going to be 2x, bless you, minus 200 minus 200, which is then 2x minus 400 there. So these are the pieces that we're going to be looking at. We're going to be looking at the x, 2x minus 400, and the 2x minus 200. Is everyone okay with how I got those? Now, what do we know about the perimeter again? Well, we know the perimeter is the sum of all the sides. So the perimeter is going to be the short side plus the middle side plus the longest side. Okay? And we can fill them in. So we know the short side, well, that's x. We know the middle side is 2x minus 400. And we know the longest side is 2x minus 200. Okay. And adding these up, what do we get for our perimeter now? When we add these up for our perimeter, we end up, when we combine the x's together, it looks like we get 5x, right, minus 600. Is everyone okay with that so far? So do you see how we're working that out? And let me know if it's not making sense. I think this is the easiest way to work these out. I like to write things out in words, then translate it to a variable, and then put it all together. Sometimes you might just jump to the variables, but then I think students forget what we're doing. And then it's easy to get mixed up. So we have our perimeter, which is that 5x minus 600. And what is our perimeter? What number is represented by the perimeter? Well, that is represented by that 2,400, right? Because perimeter is going to be that 2,400 feet there. Now we've got everything that we need. And now we can go back and finish this. So now we can finish this very easily by simply adding that 600 over. 5x now equals the 3,000. We'll divide by our 5. And now we've got x equaling 600. Is everyone okay with that so far? Now that doesn't answer the question. So here's a lot of times what happens. Students work this out, and they get this, and they write it down as an answer. But that's not going to be our complete answer. When we get an answer, we need to go back and we need to make sure that it is what the question really wants. If we go back and we look at this again, so we got x equals the 600 here, that's not going to answer our question. It's only part of it. Because on question 15 here, it says, Find the lengths of the three sides of the triangular plot. So we're going to have to find all three. So we've got one of them already. Now let's go back and look at what we know about these sides. So what do we know about the sides? Okay, the short side was x. So let's try to get these filled out here. So we know the short side is x. And what did we find x to be? 600. And let's go ahead and label that with our units. So this is something that we can measure. So it's going to be in the base unit. And in this case, our base unit is feet. So the first one is going to be 600 feet for the short side. And then we've got the middle side. And that is 2x minus 400, which is then 2 times the 600 minus the 400, right? And that's 1,200 minus 400, so that is then 800 feet, isn't it? Okay, we're going to go ahead and label these now. And what about the last one, the longest side? Okay, the longest side is going to be 2x minus 200, which is then 2 times 600 minus 200, which is then 1,000 feet. So there are the three answers for this question. We found them, we labeled them, and let's make sure it makes sense. How do we know it makes sense? Well, these should add up to give you 2,400, right? And if we add these up, do we get the 2,400 that we need? We do. Is everyone kind of okay with how we did this? So that's the way I set them up. I always like to start with words, build the equation, put it together, and then make sure we answer the question completely. And if you ever have any questions, be sure and say something. I can explain things in a different way. We can slow down. We can work through another example if we need to. So that's a geometric figure type of question. Let's look at another one. Let's look now at question 17. Anyone have any questions so far? Okay. We're going to look now at question 17. So question 17, we're looking at a storage container. And it says a storage bin is in the shape of a rectangular box. Find the height of the box. If its length is 18 feet, its width is 5 feet, and its surface area is 496 square feet. Now, why is it square feet here? Because that 496, what did it come from? A surface area, that's why it's square. All the others are not. Now we're going to try to find the height. So we've got a picture drawn, and we're going to redraw that, and then we're going to see what we've got, and we're going to figure out what formula we need to apply here. And this is on page 119 again. And we're going to be looking at question 17. So they give you this container, and we need to find the missing piece. And we know this container has a height of h, so that's unknown. It's 18 feet long, and it's 8 feet wide here. Now, what we do know is we know the surface area. And I picked this one because this one's going to make you go back to the back cover of your textbook. And the surface area is 496 square feet, but we're not going to put the square on it. Right, so it's 496, and that's our surface area. Now, when we need a formula, we can go to the back cover of our textbook. And it's going to have all the formulas that we need. And if we go to the back cover of our textbook, when we look at that storage bin, it looks like a rectangular solid. Okay? We don't need the volume. What are we looking for? Surface area. So we're going to write down our formula for the surface area, and then we're going to apply that formula to our diagram here. So the surface area, S, is 2L, or 2HW, plus 2LW, plus 2HL. So this is going to be our H here. So we're going to be finding that. H is H. We've got a length and we've got a width. So this is going to be our W, and this is going to be our L. It doesn't matter which one is which. We just plug our pieces in. We've got our formula. We're going to work it through. Now we know our surface area is S. So that's going to be represented by the 496. And then we've got 2 times H, which is the H there, times W, which is 8, plus 2 times L, which is 18, W, which is 8, plus 2 times H, which is unknown again, times L, which is 18. So is everyone okay with how I did that? And this is just plugging the numbers into the formula. So S represents surface area. We know that's the 496. Now we're going to take a moment to clean this up before we actually start solving it. So we're going to go through each part. We're going to clean it up. We're going to see what we can combine together and then solve it. So let's clean that up a bit. We've got 2 times the 8. Okay, 2 times 8, that makes it a 16. H here. And then for the next piece, what do we have? We have 2 times the 18 times the 8, and that's 288. And then we've got 2 times 18 over here. Bless you. And that's going to be 36H, and that equals your 496. Right? Now we have something that we can work with. So I'm going to combine together on the right-hand side first, the H's. So adding those together, that gives you now a 52H when we add those up, plus 288. I'm going to move that 288 over. And I always like to have the variable on the left. So on the left-hand side, I'm going to write my 52H. And on the right-hand side, we have 496 minus 288. That gives me 208. And we'll divide by our H, 52 here, and that's going to give us our H. So divide that by our 52. And what do we get H now to be? 4, isn't it? So it comes out to be an even 4. And that tells us then our height, which is what we want, is 4. And let's put the units of measure. It's not in square feet, is it? It's going to be in feet. Why is it just in feet? Because it's something that we can measure, right? Height. When you think of the height of something, it's in feet. What's your height measured in? Feet. Not square feet. It's feet. Is everyone okay with how I work through that? Every question is a little bit different, but you see the general approach is I take my time with these. Do not rush through them. You'll save time and frustration by taking your time. So I read it once. Do what now? Is there some part that I can make clear for you? Is everything kind of making sense? Okay. Yep, because these go together here, and that's where that came from. And those go together and make that piece. So we got our 4, and that's going to be our height. So that's what we wanted. We can go back and make sure we answer the question. And the question says, last part here, find the height of the box. And that's what we did. We answered the question, we labeled it, and so that's our final finished answer. Now for the next ones that we're going to be looking at and working through is we're going to be looking at the distance problems. Okay, so we just did geometric figures. Now we're going to be looking at distance problems. And when we look at distance questions and different distance problems, what we have to worry about is if they are adding together or if they are subtracting. So we're now going to look at some distance problems. Now, when I work through these distance problems, I've got to make sure that I'm careful with the direction. And so I represent these by what are called vectors. Okay, the vectors just tell me the direction. If they're going away from each other like this, okay, so two cars going in the opposite direction, that's going to be addition. They're going north and south. That's addition. If they're going towards each other like this, that's addition. Where it's different is when we talk about subtraction and the overlap. So these are all addition. Right? So if they don't overlap, it's addition. So if they never overlap, it's going to be addition. If they overlap, it's going to be subtraction. So if you have two people running a race, they overlap, and that's subtraction. So whenever they overlap, you have to use subtraction. You can also have equal. And when would they be equal? Well, they would be equal when you, like, drive to work and drive back home. Those distances should be the same. So like this, when you go to work and come back home, they should be equaling each other. So these are the three outcomes that you can have when you build these equations. They can add together, which is usually the most common one. They can subtract from each other, or they can be equal to each other when they overlap. They subtract. When they're exactly the same, they're equal. Now, when we set these up, we're going to be having to work with the distance. And the first thing that we always do is we draw our diagrams like this to see what we're dealing with. Once we understand what we're dealing with, then we build our equation, and we use that equation to solve the question and then finish out the problem itself. So let's look at a couple of these. We're going to start with question 19. So we're going to look at question 19. Now don't worry about the table. I think using the tables is confusing. Me personally, I like to draw diagrams. I think it's much easier than making a table. You can make a table, but I've taught a long time and I found students are much better without the table. So question 19. Margaret drove to a business appointment at 50 miles per hour. Her average return trip was 40 miles per hour. The return trip took a quarter of an hour longer because of heavy traffic. And we want to find out how far she traveled to this appointment. So the first thing we do is we draw our diagram, and we draw our arrows. And in this case, and this is on, again, page 119, question 19, we're going to draw our arrows. Now, when we look at this question, we're going to an appointment, and we're coming back. So she's going to go to the appointment, and then she's going to come back. And so the way I've drawn these is this addition, subtraction, or are these going to equal each other? Okay, they're going to equal each other, aren't they? Right? Why would they equal each other? Because you're going to work, and you're coming back, and those distances should be the same. Now, each of these are going to have a rate and a time, and we're going to calculate then the distance from that. So we're going to look first, bless you, we're going to first look at the morning. And we've got a rate of speed, and we've got a time. So when she goes to her business appointment in the morning, she drove at 50 miles per hour. And in the afternoon, she drove back, and she drove a little bit slower. She only drove 40 miles an hour. From this question, do we know how long it took her to get to her appointment in the morning? Is that in the question at all? Does it tell us in that problem how long it took us to get to that appointment? It doesn't, does it? So we're going to use an X. So in the morning, we don't know how long it took her to get to that appointment. That's the unknown. That's the variable X. When she comes back in the afternoon, do we know the time there? No, but we know it takes what? It takes a quarter of an hour longer. So that's going to be X plus a quarter. So is everyone okay with that so far? Do you see how I got the diagrams drawn? Now we're going to build our equation from here. So what do we know? We know that these are equal, and we're going to have to work with the distance. Now the distance is always the same. It's calculated, and the distance is the rate times the time. So the rate times the time is going to give us our distance. And we're going to have to calculate this twice. Once for the morning and once for the afternoon. And they're going to be equal to each other, right? Because these equal. So the morning distance is going to equal the afternoon distance. Okay, so let's go ahead and put these together. We're multiplying these together. So when I look at the morning, what do I know about the rate of speed? Morning's rate of speed is 50, and the time in the morning is unknown. The time is X. So the morning, when we multiply those together, is going to be 50x, right? Those just multiply together. It's the same as using the table. I think the table for many students is more confusing than what it's worth. What about in the afternoon? Rate of speed is 40. And what's the time in the afternoon? X plus a fourth. So now we've got something that we can work with. Now we can distribute through, and that 1/4, by the way, is going to cancel itself out. And if you ever have trouble with fractions, we can write them over to the side. So let's go ahead and work this out. So on the left-hand side, we've got our 50x. We're going to distribute that 40 through, so that's 40x. If you struggle with these fractions, just write them out. So that's 40 over 1 times 1 over 4 here. Okay, and we can cancel. So that 40 and that 4, well, that cancels out, and that leaves you with a 10 and a 1. So that means then we have that 40x plus 10. Is everyone all right with that so far? If I'm going too fast, just be sure and tell me. Now, we can easily solve this out. Once we get our answer, though, x is not what we want. We have to do more with it. So if we get this solved out, x is not going to be our finished answer. It's only part of it. So now I'm going to move that 40x over. And that gives you 10x equals 10. We'll divide by our 10. And now we've got x equaling 1. However, x equaling 1 is not going to be our answer. What is this? Let's make sure we label it from here. What is x? X represents the time. Okay, so x represents the time. We don't want the time, though, because when we go back and read question 19, on the very last part here, the very last sentence, it says, how far did she travel to the appointment? This is our time. We want the distance. So we need to find the distance. How do we do that? Well, let's go back and look at the morning. Okay, in the morning, bless you. In the morning, her rate of speed was 50, and the time was x, but we now know that x is 1. And we want the distance, and so the distance is again the rate times the time. And what's my rate of speed? 50. Time is 1. That then gives me 50. And let's label it. Bless you. And the distance is 50. What are my units going to be? Well, distance is a unit of measure, the basic units. Miles per hour. So the distance is going to be in miles. So we want to know how far it was to her appointment. We worked it out, and we got the 50 miles. Okay? So it's not 1. We have to take that 1 and plug it back in to get the 50. Now, in some cases, they might want the time. And if they did, we would have been done. This one, they specifically wanted the distance. And so we calculated it out by plugging it back in. Let's try another one of these. A little bit different here. Question 22. I'm going to try to pick one of each type. So there'll be one that's addition, one that's subtraction, and we just did the equal where they were the same. And let's look now at question 22. And these are not difficult, it's just getting them set up correctly. So that's going to be the main thing. Two planes leave LA at the same time. One goes south to San Diego, the other heads north to San Francisco. The San Diego plane flies at 50 miles per hour slower than the San Francisco plane. In a half of an hour, the planes are 275 miles apart. What are their speeds? So the first thing we look at when we work with one of these is we need to make sure that we draw our diagram correctly. So we're going to start here in LA. So this is where we start. We know one heads north and one heads south. So when we read this, it says one heads south to San Diego. So that one's going south to San Diego. And the other one's going north to San Francisco. Each of these, again, is going to have a rate and a time. And while you're working on this, do you think this is going to be addition or subtraction? Which one? Addition. Okay. Why is it going to be addition? Because they go in opposite directions. And do these overlap at all? No. If they overlapped, it would be subtraction. This is addition. So I always like to note that over the side that this is going to be addition. And let's see what we've got here when we look at this again. Okay, it says the San Diego plane flies 50 miles per hour slower than the San Francisco plane. So, do we know the speed of the San Francisco plane? No, that's our unknown x. What about the San Diego plane? What do we know about it? It's 50 miles an hour slower, so that's going to be x minus 50. Okay, so the San Francisco plane is x. The San Diego plane is x minus 50. In 1/2 hour. So what do we know then? Half hour, what does that mean? Okay, they leave at the same time. So how long is each one of them in the air for? It says in a half hour. So each one of these is in the air for a half hour. So the time on both of these is going to be a half. And then the part we haven't talked about yet is the distance. And we know our total distance is that 275. Okay, so there's our 275, and that's going to be our total distance. Now we can use this to build our equation. Again, distance is the rate times the time. So rate times that time is the distance. And I'm going to go ahead, before I forget to, and pass out the sign-in sheet again. So make sure to find your name on the sign-in sheet here. And it should be on those first 2 pages. The third page is my next class. But back here we're looking at our distance. And distance is the rate times the time. And so we're going to do each of these. We're going to add them together. So we're going to add these together, and we know our total distance is going to be that 275. So that's going to go there. And the San Francisco plane, what is it? Well, it's a half times x, so that's 1/2 x. They just get multiplied together. The San Diego plane is 1/2 times x minus 50. There's our equation. Distribute that 1/2 through. So make sure you use parentheses and distribute it through. And now we get 1/2 x plus 1/2 x. And then what's half of 50? Well, half of 50, when we distribute it through, half of 50 is that 25. So that's a minus 25. That equals 275. And no need to clear out our fractions, because a half and a half, what does that add to give you? Half and another half makes it a whole. So a half of an x, another half of an x, that makes it a whole x. And that's going to be minus 25 equals that 275. We're going to add our 275, or sorry, add that 25 to each side. And now we've got x equals 300. So that's part of our answer, and we need to make sure that we answer it completely. And so what does it want? We want to find the speeds of both of the airplanes. So we need to find the airplane speeds. So we've got that 300. Let's make sure we can now get the 2 speeds. So let's look and see what we've got with our diagram here. Now we know our x was 300, and that represents the rate. And we're going to look first at our San Francisco plane. Our San Francisco plane, its rate is x, so that's going to be 300. And it's measured in miles per hour. So there's the first answer. The next one, what about the San Diego plane? What is its rate? Well, its rate is x minus 50. So that's 300 minus 50. And that's going to now give you the 250 miles per hour. We've answered the question. We labeled our answers. And so that's what we needed to do. A lot of these are just difficult in the setup. Once you get the equation, that's the easy part. It's then actually making sure you answer that question and labeling that students sometimes struggle with as well. So we've done addition and we've done equals. Now let's do one where we subtract. And then we'll look at investment and mixture problems after that. So 23. Okay, 23 is going to be a subtraction question. In the Apple Hill Fun Run, Mary runs at 7. Janet runs at 5. They're going to start at the same time. And we want to know how long it will be before they are 1.5 miles and 1.5 miles apart. When I draw these arrows and they're going to overlap, I always make sure I draw the larger one first. The faster person always goes on the top. So we've got Janet and we've got Mary. And Mary's the faster runner, so she'll go on top. And Janet is the slower one. And these overlap. So that means then it's going to be subtraction. And let's work with each of these. We've got a rate and a time for each one. And this is actually very easy to solve and easy to work with. And there's a question just like this in your homework as well. There's only 2 distance questions. One of them is like 22, one of them is like 23. So Mary runs at 7 miles an hour. So that means her rate is going to be 7 here. And Janet runs at 5. So 5 is going to go here. Do we know the times of either one of these? Nope. So we're going to use an X for both of them. We said it was subtraction. And so that means Mary minus Janet for the distance is going to equal the distance apart. And again, how do we find our distance? Our distance is always the rate times the time. So very easy to solve this one out. There's not much to this one. Much simpler than the last one. Bless you. So when we look at Mary, what about Mary? Mary is 7x, right? Because we multiply those together. Janet is 5x, so that goes here. And it tells us from the question that they need to be 1.5 miles apart. So we're going to put the 1.5 right here. Now we can easily solve it. We've got 7x minus 5x. That makes it a 2x. And that equals 1.5. We'll divide by our 2. And that leaves us now with x equaling 3, I believe, isn't it? Or not 3, 0.75. We've got 1.5, we're going to divide that by 2, and we get 0.75. And we can use a decimal because there's decimals already in the question. Is that going to answer it for us? Okay. What does x represent? Let's make sure we know what x is. X is the time. Is that what we want? Yes, it is. So how do we answer this question then? X is what we want. We want to know what the time will be. So the time then is 0.75 hours or 45 minutes. And I would take either one. So you can represent that time as 0.75 hours, or you can use 45 minutes. They are the same. So I would take either one. Is everyone okay with that? That one was subtraction. Now we're going to move on, but we're going to look at the mixture and the investment questions next. And they're going to be done in a very, very similar manner to the distance ones. Except instead of having a distance, we're going to have a pure for the mixture questions and an interest for the money type questions, for the interest problems. So let's now look at a couple of mixture questions. And once you can do the mixture, the investment ones are the same. And when we mix chemicals together, we have to look at the concentration and the amount. So the percentage rate and how much is actually in them. And we're going to do a couple of these. So let's look at we'll do question 31 on page 121. So Aaron wishes to strengthen a mixture from 10% alcohol to 30% alcohol. How much, here's a key word here, pure alcohol must be added to the 7 liters of the 10% mixture. So whenever I work with these mixture or the investment questions, I draw a diagram. This is question 31. And I label them 1, 2, and 3. And 1, 2, and 3. And the way I remember it is 1 plus 2 is 3. And 3 is always what we want. And 1 is going to be what we're going to start with. So we're going to start with some chemicals. We're going to either strengthen or reduce them down with another set of chemicals to get out what we want. So let's see what we've got. Each of these has an amount and a percentage rate. So an amount and a percentage rate. Aaron wishes to strengthen a 10% mixture to a 30%. So let's just take that part there. Aaron wishes to strengthen a mixture from 10% to 30%. So that means I'm going to start with a 10% solution. Okay, because that's what I'm going to start with. I'm going to strengthen it, and I want to end up with a 30%. So start goes here. Box 3 is always what you end up with. So we want to end up with a 30% solution. And we're going to do that by mixing in some pure. Now let's look at the amounts. How much pure alcohol should be added to 7 liters of a 10% mixture? So the 7 liters of the 10%, that's going to go here. It doesn't tell us how much pure we have. So for the pure, we have an unknown amount X. So we don't know what that is. But when I talk about pure alcohol, what's the concentration as a percentage? Okay, pure, if it's pure water, it wouldn't have any, it would be 0. Right? But in this case, we're looking at pure alcohol, so the percentage rate would be 100%. If you use water to dilute something down, it's 0. If you use pure alcohol, in this case, or pure insecticide, that's 100%. Now, what I remember is 1 plus 2 is 3, so these amounts add across. 1 plus 2 is 3, so these go together, and that makes it 7 plus x here. Now, once we have this diagram, we can easily make our equation. And we're going to use the pure, just like the distance. Pure is the amount times the rate. Okay, so pure is the amount times the rate. We're going to build our equation from these boxes here. And 1, 2, and 3. And again, the way I remember is 1 plus 2 equals 3. So they're going to add together to give you that third one. When we work with these percentages, we have to convert the percentage to a decimal. So when we talk in our first one, amount is 7, percentage rate is 10%, so that's going to be 7 times 0.1, right? So those get multiplied together. Now what about the next one? 100%, that's 1, because that's 100%, and the x there. The only reason I'm putting the 1 is so if you come back later, you're going to see that that 100% is the 1 there. And what about on the other side? On part 3, percentage rate is 30%, so 0.3. How much is in there? 7 plus x or x plus 7, same thing. Now it's just a matter of solving it out. So 7 times 0.1, that is 0.7. 1 times x is just x. And now we can distribute that 0.3 through. And that is now 0.3, or sorry, let me write it out first. Yeah, well, either way, write it out. And we'll just distribute through 0.3x. And then 7 times 0.3, that should be a 2.1, I believe. We'll distribute that through, and I'll just write the x first. So that's going to be your 2.1 there. Now we can finish it. So subtract off the 0.3x. And subtract off the 0.7. Sometimes it's helpful to put the 1 in front when you work with decimals so you don't make a mistake. So I'm going to put the 1 there so I don't accidentally add wrong on the x's. Those cancel. And 1 minus 0.3, well, that is 0.7x there. The other side, putting those together, 2.1 minus 0.7. Should be a 1.4. We're going to now divide by our 0.7. And that leaves us with x equaling now, it looks like 2. Now we need to make sure we answer the question. What does that x go with? X was the amount of the pure. That's what we want. Okay, we need to make sure we label it with the correct units. And what was this in? This is a volume on these. These are in terms of liters. So what do we have for our answer? We have 2 liters at 100%. And I always like to label it with the unit of measure and also the percentage. So it's 2 liters at 100%. Is everyone kind of okay with how I work that one through? Uh-huh.
For the second substance there, why did you make it 100%?
Okay, which one are we looking at? This one?
You have the first part of the second one.
Okay, here? Okay, yep, this part. Okay, you're looking at this part, right? Okay, so this one, they said there was 7 liters at the 10%. This one we said was pure. Did it tell us how many liters of pure that we had in that question at all? It didn't, did it? So that's going to be our unknown now. And that pure is 100%. Okay, so that's why we use the 100 there. Now, when we look at box 3, these always add across. So 7 plus x, those go together, and that makes it 7 plus x there. Does that answer your question? Okay, yep, so just remember, we don't know, so something's going to have an x with it. And they always add across. And then you use that then to build your equation from the pure, and then eventually solve it and get our final answer with the 2 liters at 100%. Okay? We're going to do another one of these too. And you'll also see a similar type of question in the investments. We just did a mixture one with the pure. Let's look at another one. I think the pure was a little bit easier. So I'm going to go back and we're going to look at question 30. So I did 31 first because the pures I think are easier. Well, actually we don't have to go back to 30. We'll do 32. Yeah. Well, I want to do two different ones. We'll go back to 30. So let's look at question 30. We don't need to worry about the table. I don't like the tables. I think the tables make it more confusing. So don't worry about the table on this one. But let's read this one. We're going to do 30. This one's more complicated, and that's why I did the other one first. A student needs 10% hydrochloric acid solution for a chemistry experiment. How much 5% acid should she mix with the 60 milliliters of a 20% to get the 10%? What we need to make sure on these is that the percentages go in the correct boxes. And this one is a little bit more difficult than the last one. And that's why we switch them around. The textbook is a good textbook, but sometimes they put easier questions at the end than at the beginning. So let's see what we've got here. When we look at these percentages, we have to make sure that they go in the right place. So a student needs a 10% hydrochloric acid solution. So box 3 is always what we want or need. So that 10%, it has to go over here. Okay, it has to go over there because that is what we want at the end. When we mix these chemicals together, we have to make sure that we get 10%. Now, what does that 10% come from? Well, let's see what we start with. So we want to get this 10%. That's our goal. 10% solution. And it says, how much 5% solution, acid solution, okay, so the 5% is going to go here, do we need when it's going to be mixed with 60 milliliters of a 20%. So is everyone okay with that so far? So we've got all of our percentages labeled out. This is what we start with. This is what we're going to add to it. And this is what we want to end up with or we need to have. The 5%, do we know how much 5% we need? Nope. So we're going to use an X. Now we always add across. So these add across. And so that's X plus 60 here when we add across. And now we build our equation. And again, we're going to look at the pure. And the pure is the amount times the rate. So we're going to add across here. When we make our pure, we multiply. So let's look at our first one. 5%, that's going to be 0. Watch your decimals here. 0.5x plus 60 times 0.2 equals 0.1 times x plus 60. Now we can distribute through, and we should be able to easily solve this out. So distribute through here, 0.05x, and we've got 60 times 0.2. That should be, I believe, 12, but I always double check things. Yep, that's 12 there. The 0.1 gets distributed through. And that is then 0.1x. And 0.1 times 60, that's a 6. Combine. So move over that 0.1x. And move that 12 over. Put those together, and we get 0.05 x, and it's going to be negative, because we subtracted here. The 12s can cancel. The 0.1x's can cancel. And 6 minus 12, well, that's a minus 6. You've got to watch your signs there. Divide by your minus 0.5 on each side. And we know the double negatives cancel, making it positive. And 6 divided by 0.05, well, that comes out to be, now negative and negative makes it a positive 120. I do what now? Okay, now, what does x represent? Okay, we got 120, and what does that go with? Where did the x belong? Which one had the x in it? The x had the 5%, right? And that's what we wanted to find. We wanted to determine how much of this 5% we need to pull off the shelf. Because we've got the 60 liters here already at 20%. And we want to get a 10%. So I've got to go back to the shelf, and I've got some 5% solution sitting there. How many liters do I need? Well, I go back, and we found that x to be 120. So if I was going to do this, I would go pull 120 liters. Or is it milliliters? Let's see here. For question 30, it is milliliters. So I'd pull 120 milliliters and mix it with the 60, and that would give me the 10% that I need. So that's what we want. So what's our answer going to be? Well, our answer is going to be 120 milliliters. And what's it going to be at? It's going to be at that 5%. And that's what we wanted. And that's what we go pull out of the supply cabinet. Okay, does that make sense now? Okay, yep. And if not, make sure and say something, because I can explain things again in more detail if I need to. So those are the mixture questions. Now we're going to look at investment. And investments are going to work the same way. Probably do one, maybe two of these. We'll see how much time we have. Let's look at one of these. How about we look at question 39. So this is going to be our investment question. So we'll look at question 39. And it's basically set up the same as the investment, or as the mixture was. Zuhu inherited $200,000 from her grandmother, and she gave 30% to her favorite charity. And then she invested some at 1.5% and some at 4%, and she earned $4,350 per year. And we want to know how much she got at each rate. So what we're going to do is we're going to set this one up the exact same way that we would have set up the mixture questions, except instead of having containers, we're going to use dollar signs to represent the money. This is going to be our total amount over here. And again, 1 and 2. Now we need to figure out what we're actually working with. So she inherited $200,000. And she gave 30% to the charity. So we started with $200,000. And then that gift is going to be 30%. So she gifted away 30%. So that's 200,000 times 0.3. And so she ended up giving to charity now 200,000. Type in here correctly. Okay, so 200,000. And she gave 30% of that to charity, so that's 60,000. So she gave 60,000 to charity, and how much is left to invest? that's going to be 200,000 minus that 60,000. So she's going to be left with 140,000. And that's going to go over here under my total amount. So we've got 140,000 for my total amount. So is everyone okay with that? So the first thing we did was we read it. We figured out that we needed to go through and give that charity amount away and then see how much we had left. So we ended up with 140,000 to actually invest. So that's going there. Okay, and we're going to invest it in two different funds. We've got one at 1.5%, and the other one's going to be at 4%. Do we know how much money went in the 1.5%? Does it tell us at all? No. So we're going to use an X. What about the second one? Do we know how much is in here? No. But we can't just use the X again. So the second one is going to be the total amount minus X. So that's going to be 140,000 minus X. Why is it 140,000 minus X? Well, these need to add together to give you that 140,000. And what happens with a positive X and a negative X? When you add them together, they're going to cancel out. So if I looked at it like this, is the total minus X. So one's X, one is the total minus X. That gives you 140,000 together, right? Because one's going to cancel out with the other one. Now we build our equation. And our equation is going to be built the exact same way that we did the last one with the pure. But we're looking at interest. And your interest is the amount times the rate. Okay, so the interest is the amount times the rate. Or not total amount, total interest. So let me scratch that up because this is going to be my total interest. Now, where students get confused is the interest versus the total amount. Interest is how much money I make. The total amount is how much money I have in the account. When I have a savings account, there's three things that are involved with it. How much money you actually have in that account, the percentage rate that it pays out, and how much money it makes in interest. So they're completely different. The interest is going to be way less than how much I have. Because I might have $10,000 in the account, but I might only make $100 in interest, right? So interest is always going to be the smaller one. So when I look at my first one, we multiply. Watch your decimals here. So 1.5%, well, that's going to be 0.015, and we have to multiply that by the X there. The next one is going to be 0.04. Let me move this over here, and we've got to multiply that by 140,000 minus X. So there's that. And what is it going to equal? Now, it's not going to equal 140,000. How much money did we make? She made $43.50, right? And that is from the question itself. So she made $4,350. Now we can finish it. So let's go ahead and finish this out. And then I want to look at a homework question. And then that'll be it for today. So let's go ahead and finish this one out. So we'll distribute that 0.04 through. Okay, so that's going to be 0.015x. That's going to now be, when I distribute through, bless you, 5,600. And now we have a minus 0.04x. And that equals your 4350. So all we did there was I just distributed through. Be careful again with these decimals when we combine them together. Watch your signs and watch how they go together. 0.04 is the larger one and it's negative, so we subtract them. So that's going to be a minus 0.025x. And then we've got that plus 5,600. That equals your 4,350. Move that 5,600 over. Minus 0.025x equals, when we subtract here, equals a minus 1250. We're going to divide. And what happens when we take a negative divided by a negative again? It's going to make it positive, isn't it? And what does that come out to give us now? That comes out to give us now, x is going to be the 50,000. Okay. Now, we need to get both of these funds. So which one did x go with? So we got x to be 50,000. So x is the 50,000, and it went with the 1.5%. So let's go ahead and get our answers. And then I want us to look at one homework question quickly here. So we'll finish this one up. We'll look at one homework question. Okay, so we got the 50,000. So what do we know? We know we have $50,000, and that's going to be at 1.5%. So that's the first half of this question. And what about the other one? Okay, we need to get the other one, and the other one is the total minus x. So the other one is 140,000 minus that 50,000. All right, and that then comes out to be $90,000. And that is at 4%. So we've got 50,000 and we've got 90,000. We labeled them with the correct percentages. Is everyone okay with how I did that now? I want us to look at one quick question here from our homework, and then that'll be it for today. There's two questions, 9 and 10, that are questions where you need to plug numbers in. I'm going to work out question 10 for you, and you can look at question 9. So these are from your homework. I'm going to work out question 10. You can do question 9. Now for 9 and 10, all you're going to have to do is plug in the needed number and work it out. So on question 10, it says your home state uses this linear model to predict the number of vacationers, y, compared to the temperature for that week, x. We want to find the number of vacationers predicted for a week when the average temperature is 85 degrees. And so this is 1.2, and we're going to be looking at your homework. We're going to be looking at question 10. Here's your equation. Y equals 24 times x minus 70 plus 1274. And x is going to be the temp. Now, all we need to do on this one and 9 as well is plug in the number. Okay, so we are given a temperature of 85 degrees. So that means we're going to have to plug in the 85, right? So all you need to do is plug in the number for the variable that they give you. So we're looking at the temperature. We're going to try to find the number of vacationers. So we plug in our 85. And then we'll work this out quickly here. That gives us 24 times that 15 plus 1274. And we add those together. I think you kind of know what to do. You just multiply it out, add them together, and that gives you 1,000 634. And this is going to be vacationers, because this is Y, right? All of these are Y here. And Y is vacationers. So that's what we're wanting to do. So Y is going to be the number of vacationers. And that's what we found. And that answers the question. So make sure that you've signed that sign-in sheet. I know that should be around here somewhere. So please, before you leave, please make sure you sign that sign-in sheet. I'll see everyone on Tuesday. And what's your homework now? Your homework is 1.1. You're going to want to finish it if you haven't done so. And 1.2. You're going to want to finish that as well. Okay? I will see everyone then on Tuesday. But again, make sure you sign that sign-in sheet. And if you ever want to see the notes, I post them in Canvas right after class, along with the videos too. So you can always download the notes if you think you missed something.